All right, in this video we discuss a fun little connection between Pascal's triangle, Fibonacci numbers, and generating functions. So let's begin with Pascal's triangle. So just as a reminder, the way we draw this triangle is we put a 1 at the top, then the next row is two 1s, and then the next row I write a 1 and a 1 on the end, and in between these two 1s I put 1 plus 1, so that's 2. I write my 1s at the end for the next row, and then in between I put 1 plus 2 is 3, and 2 plus 1 is 3. I put my 1s at the end for the next row, then I write 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and I continue downward like that. So this is Pascal's triangle, and it's often defined in terms of binomials, so we'll convert this into binomial notation in a second. Okay, so what are we going to do with Pascal's triangle? Well, I'm going to highlight certain entries. I'm going to go down certain diagonals in Pascal's triangle. So first I'm going to highlight 1, and I'll write that 1 is equal to 1. Great. Next, what I'll do is I'll highlight this one, and then I'm going to go down a row and over 1. So I'm going to go all the way down this. I'm going to go down a row, and I'm going to skip the 2 and move over to the 1. And I'll notice that 1 plus 1 is equal to 2. So I add those two 1s. The next thing I'm going to do is start with the next one. I'm going to go down a row and over 1, so I'll get to 3. And then I'm going to go down a row and over 1, so I'll get to 1. And I'll notice that 1 plus 3 plus 1 is equal to 5. Okay, and I'll continue this pattern, right? I'll go to the next one. I'll go down a row and over 1 to the 6. I'll go down a row and over 1 to the 5. And I'll go down a row and over 1 to the 1. And I'll notice that 1 plus 6 plus 5 plus 1 is equal to 13. And let's try this for one more. I will start with this one. I will go down a row and over 1 to 10. Go down a row and over 1 to 15. Down a row and over 1 to 7. Down a row and over 1 to 1. And I'll see I get 1 plus 10 plus 15 plus 7 plus 1 is equal to 34. Another question you might ask is, well, what's the big deal? I'm taking these sums and I'm getting these numbers. Well, the thing to notice here is that 1 is actually the first Fibonacci number, the 0th Fibonacci number, f0. 2 is the Fibonacci number, f2. 5 is the Fibonacci number, f4. 13 is the Fibonacci number, f6. 34 is the Fibonacci number, f8. And again, here I'm defining the Fibonacci numbers. I'm assuming f0 is equal to 1, f1 is equal to 1, and I'm taking fn to be the sum of the previous two Fibonacci numbers, fn minus 1 and fn minus 2. So for example, f0 is 1, f1 is 1, f2 is 1 plus 1, so that's equal to 2. I'm adding the two previous numbers. f3 is 1 plus 2, I'm adding the two previous numbers, so that's 3. f4 is now, I'm going to take 2 plus 3, so f4 is 2 plus 3, so that's 5. f5 is now going to be 3 plus 5, so that's going to be 8. f6 is going to be 8 plus 5, so that's 13. f7 is going to be 8 plus 13, so that's 21. f8 is 21 plus 13, so that's 34, and so on and so forth. So I have my Fibonacci numbers, and I notice this connection, and then the question I'm going to ask is this connection true in general, right? Does this keep going? So the first thing we're going to do is to kind of write down a formula that we want to prove. We're going to have to use binomials, and then we'll prove that the formula holds using generating functions. Okay, so Pascal's triangle can be rewritten in terms of binomials. And what is a binomial? A binomial is an expression of this form. This is pronounced n choose k, and this symbol is defined to be n factorial over k factorial times n minus k factorial for n bigger than or equal to 0 and k bigger than or equal to 0 and less than or equal to n. And we'll take 0 factorial to equal 1. So when I write 0 choose 0, this is going to equal 1. It's 0 factorial over 0 factorial times 0 factorial. If I plug into my definition, 1 choose 0 is going to be 1. 1 choose 1 is going to be 1. 2 choose 0 is going to be 1, 2 choose 1 is 2, and 2 choose 2 is equal to 1, and so on and so forth. So the numbers in Pascal's triangle can be replaced by these binomials, and you might recall that Pascal's triangle has this property that if I take 2 choose 0 plus 2 choose 1, for example, I should get 3 choose 1, right? The idea being that 1 plus 2 was equal to 3. Or, for example, that 3 plus 3 should equal 6. And this property can be summarized in the following equation, that n choose k can be written as n minus 1 choose k minus 1 plus n minus 1 choose k. So the n's keep track of which row we're on. and the k keeps track of which entry in that row. Okay, so what might we notice? Well, let's color code just like before. So this first guy is 0, choose 0, and the next color coding we did was we chose this one, and then we went down a row and over one to choose this one right here. Then we chose this one, we went down a row and over one to choose 3, choose 2, and then down a row over 1 to choose 4, choose 4. And then the same thing with the following: 3, choose 0, then down a row over 1, then down a row over 1, and then down a row over 1. Okay, so what did we get? Well, we should have that 0, choose 0 is F2, 1, choose 0 plus 2, choose 2 is F4, 2, choose 0 plus 3, choose 2 plus 4, choose 4 was F6, and 3, choose 0 plus 4, choose 2 plus 5, choose 4 plus 6, choose 6 is equal to F8. And what do we notice about each of these? In each of these, we notice that the number at the top is always being incremented by 1. So here we have this pattern 3, 4, 5, 6. While the number at the bottom is being incremented by 2. Okay, so we can kind of summarize this in an equation, right? We notice that this is true for all of them. This bottom number here is being incremented by 2. This top number is being incremented by 1. And how can I summarize this? Well, I can actually write down this as a conjecture. So I'll write that the sum of m plus n, choose 2n. So notice that I'm starting with m at the top and incrementing it by 1 at a time. So n equals 0, I have m, choose 0. When n is equal to 1, I have m plus 1, choose 2. When n is equal to 2, I have m plus 2, choose 4. Right? So the top is being incremented by 1, the bottom is being incremented by 2, and my conjecture is that this is going to equal the 2mth Fibonacci number. Okay, so let's prove this. Okay, so in order to prove this, we're going to need to derive a generating function for the Fibonacci number. So I've written down the definition of the Fibonacci numbers here. It's the recursion that defines the Fibonacci numbers. And what is a generating function? Basically what I'm going to do is I'm going to take this element of the sequence, fn, and attach them to powers of a variable x. So I'm going to define a power series. So this is going to be a formal power series. It's going to be the sum of f sub n, x to the n, where n is bigger than or equal to 0. So this is a formal power series in the ring C bracket bracket x. All right, so we'll view this as a formal power series. And again, what am I doing? I'm essentially just saying that this guy right here is equal to f sub 0 plus f sub 1x plus f sub 2x squared plus f sub 3x cubed, so on and so forth. So attached to x to the n is the nth Fibonacci number. Okay, so let's try to find a nice formula for f of x. So one thing I know is that f of x, again by definition, is the sum of f sub n, x to the n, where n is bigger than or equal to 0. And so what I'm going to do is I'm going to detach from this sum the n equals 0 and n equals 1 term. So I could write this as 1 plus x plus the sum of f sub n, x to the n, where n is bigger than or equal to 2. Okay, now whenever n is bigger than or equal to 2, I can use my recursion. So I'm going to do just that. I'm going to write this as 1 plus x plus the sum of f sub n minus 1 plus f sub n minus 2, x to the n, where n is bigger than or equal to 2. Okay, so where does that get me? Well, let's split these guys up. This is going to be 1 plus x plus the sum of f sub n minus 1, x to the n, plus the sum of f sub n minus 2, x to the n. Here n is bigger than or equal to 2. Here n is bigger than or equal to 2. Okay, and what am I going to do now? From this first sum, I'm going to pull out an x to the 1, and from the second sum, I'm going to pull out an x squared. So this is going to be 1 plus x times the sum, n bigger than or equal to 2, of f sub n minus 1, x to the n minus 1, plus x squared times the sum, n bigger than or equal to 2, of f sub n minus 2, x to the n minus 2. Okay, so let's clean this up and make a little bit more room to continue working with this. Okay, so now I'm going to take these two sums and re-index them. So with this sum, I'm going to replace every single n minus 1 with n, And with the second sum, I'm going to replace every single n minus 2 with n. Okay, so when I reindex this, what does this become? This is going to become 1 plus x times the sum of f sub n, x to the n. And the thing to notice here is that in this first sum, the first power of x that occurred was x to the 1. So the first term in this series is f1 x to the 1. So I want to make sure that the first term in this new series is f1 x to the 1. So I'm going to start this series at 1. So this is the sum n greater than or equal to 1. And then I'm going to do the same thing for the second series. I noticed that the first term here was f sub 0 x to the 0. So I'm going to start this second series at n equal to 0. So this is n greater than or equal to 0, f sub n x to the n. Okay, and now what do I notice about these two series? Well, the first thing I notice is that this guy right here, this guy is just f of x. All right, this is my original series, f of x. What do I notice about the second guy? This guy is just f of x, but I've chopped off the n equals 0 term, right? So this guy right here is just f of x, but I've chopped off the n equals 0 term, so I've chopped off 1. Okay, so what am I looking at here? I'm looking at 1 plus x times f of x minus 1 plus x squared times f of x. Okay, so if I simplify this, I'm going to get 1 plus x times f of x plus x squared times f of x. Okay, so now I have this very nice recurrence for f of x. So let's clean this up and see where this gets us. Okay, so this is the recurrence that I found. I found that f of x is equal to 1 plus x times f of x plus x squared times f of x. And if I solve for f of x, I actually get this really nice expression. I get f of x is equal to 1 over 1 minus x squared. Okay, so what is this telling me? It's telling me that, again, I'm viewing this as a formal power series. And this is telling me that f of x is the multiplicative inverse of 1 minus x squared inside of this ring of formal power series. Okay, and the thing to remember is that the multiplicative inverse of 1 minus x squared is going to be a power series, so it's going to be an infinite sum. And in particular, it's the infinite sum given by f sub n x to the n, where n is greater than or equal to 0 by definition. Okay, and so to get our result, we actually need to recall two basic facts. First is that when we look at 1 over 1 minus y, we're looking at the multiplicative inverse of 1 minus y in the ring of formal power series, and this is just our geometric series. So 1 over 1 minus y is going to be interpreted as the sum of y to the n, where n is bigger than or equal to 0. And the other thing we need to recall is our binomial formula. So x plus y to the n is just given by the following formula. So it's the sum of n choose k, x to the n minus k, y to the k, where k goes from 0 to n. And here we're assuming that n is a positive integer, or n is a natural number. Okay, so where does that get me? Well, here's the interesting thing. I have that, again, remember my generating function. This is my f sub n, x to the n, where n is bigger than or equal to 0. We called this f of x. And we just showed that f of x is equal to 1 over 1 minus, we could rewrite the denominator as 1 minus x plus x squared. Okay, and we can use our formula for the multiplicative inverse of 1 minus x plus x squared. So this is going to be the sum of x plus x squared to the n, where n is bigger than or equal to 0. Okay, so I'm using this equation where y is equal to x plus x squared. And now what I can do is I can use this binomial expansion to try to figure out what x plus x squared to the n is. Okay, so let's continue. So this is going to be the sum, where n is bigger than or equal to 0, of the sum of n choose k, k going from 0 to n, of x to the n minus k times x to the 2k. And then I might notice that this is equal to the sum n bigger than or equal to 0 times, well, of the sum k going from 0 to n of n choose k, and then x to the n minus k times x to the 2k is just x to the n plus k. Okay, and we'll need one more fact. We'll need to remember that n choose k is always equal to n choose n minus k. So I'm going to rewrite f of x in the following way. I'm going to get that f of x can be expressed as the sum, n bigger than or equal to 0, of the sum, k going from 0 to n, of n choose n minus k times x to the n plus k. And again, remember, this was originally defined to be f sub n, x to the n, where n was bigger than or equal to 0. Okay, so what are we after? We want to find a formula for f sub an even index. So I want to find the formula for f sub 2m. So I know that the coefficient of x to the 2m on this side is f sub 2m. So now the real question is, what is the coefficient of f sub 2m in this formula? So let's figure that out. Okay, so I've taken the time to clean this up and rewrite our question. So I'd like to know, what is the coefficient of x to the 2m? On the right-hand side, I know it's going to be f sub 2m. So the question is really, what is the coefficient of x to the 2m in this middle sum? Is there a nice formula that comes out of this? Well, the answer is going to be yes, but let's try to figure out what that formula is. So what I'm going to do is I'm going to collect all the x to the n plus k, where n plus k is equal to 2m. Remember, I want the power of x to be 2m, and I know that n has to be bigger than or equal to k has to be bigger than or equal to 0. So that's how this information can be summed up over here. Okay, so let's do that. Well, let's analyze this stuff first, right? Let's analyze this stuff first. What is this telling me? Well, I know it tells me that k can be written as 2m minus n, and so n greater than or equal to k greater than or equal to 0 becomes n greater than or equal to 2m minus n greater than or equal to 0. Okay, so what is this telling me? This is telling me that n is bigger than or equal to 2m minus n, and 2m minus n is bigger than or equal to 0. So what does that tell me? That tells me that 2n is bigger than or equal to 2m, and 2m is bigger than or equal to n. And then I notice that this first 2n greater than or equal to 2m can be written as n greater than or equal to m, and 2m is greater than or equal to n. So I can summarize all of this information as n has to be between m and 2m, right? Remember, m is fixed. Okay, so to sum this up, we have that if k is equal to 2m minus n, and n is greater than or equal to k is greater than or equal to 0, that means that n has to be between m and 2m. And remember, m is fixed here. So now I can ask myself, what's the coefficient of x to the 2m? Well, from our sum above, it's going to be all the terms n, choose n minus k, where I have that n plus k is equal to 2m, right? Remember, we want the power to add up to 2m, and n is bigger than or equal to k is bigger than or equal to 0. But we've just shown that this can be rewritten as n, choose n minus, k can be replaced by 2m minus n, and this condition can be replaced by n going from m to 2m. Okay, so I have the sum. Let's clean this up a little bit. This is n, choose 2n minus 2m, where n goes from m to 2m. And we're almost there. So this is going to be my coefficient of x to the 2m. Okay, so we can clean this up just a little bit more. We can write this as the sum n going from m to 2m of n, choose 2 times n minus m. And then what I can do is I can reindex. I will replace n with n plus m, and this sum is going to become n plus m, choose 2n, n going from 0 to m. Okay, and we've proved our result because this is the coefficient of x to the 2m, and we know that the coefficient of x to the 2m on the right-hand side is f sub 2m. So this proves our conjecture. So it's kind of neat. And so we've used generating functions to prove this conjecture.